Greetings 216ers, this is Professor Kaufman, and what ensues is a overview of Project 2. This involves 3 separate problems. They're all distinct and unrelated to one another, so theoretically you could tackle them in any order, maybe 2, maybe 3, then 1, but it's recommended that you work in sequence as was before. They each deal with a slightly different domain associated with things that we've talked about in class at this point. The first problem deals with bit level operations and emulates what amounts to an embedded programming setting that simulates a little thermometer. And the next problem deals with use of the debugger in a little puzzle box program. It's not a typical program, as we'll talk about in a second, but instead is designed specifically to get you to exercise features of the debugger to move through the phases and earn points. And then the final problem is more or less a traditional programming exercise in which you'll put together a small interactive Hashmap application. And this will build upon the complexity of the previous programs you did in Project 1, just basic C applications to manage the data structure in a similar fashion to what was done in one of the earlier labs. And we'll make that connection shortly later. Okay, let us get started with some basics. And as in other cases, it's a good idea to grab the code pack out of the gate. So I'll do so here. Give myself a copy of the link address and buzz over to my editor. This is the directory listing. You can see I've got some various codes from previous stuff over here. Not Project 2 yet, so I'll grab that here. Paste the link in with the wget. This will work if you're on Grace to download the code quickly. And if I refresh the directory listing, I got my P2 code here. So I will unzip p2 code.zip, and that should create a directory here that's full of the goodies. And over here then is the stuff that's been provided. It includes a make file and various testing things here. Let's see. Yep, I think that's all of them. That's good. Okay, cool. So I'm going to change into that. And one of the first things that you might notice is that if you, for instance, tried to just make and run the test prob 1, it's not going to build. And that's on account of it's actually your job in this case to create some of the C files that are necessary for this one to run. And building the first project, or the first problem on the project here, this is part of what we'll talk about in a moment. So the first problem then requires you to create this file. Let's see, it's a thermalupdate.c, and you'll need to copy various things in it. There's a quick and expedient way to do so that I'll get to in just a second, but it'd probably be a good idea to talk about what the problem was about first. So it may come to pass that some of you are involved in embedded programming small CPUs, not desktop or server class stuff, but devices like thermometers or watches or anti-lock brake systems in cars and so forth. This has a somewhat different character to it, but is oftentimes done in C, in rare cases in assembly as well, but most often in C these days. And this problem is based upon experience at a past university where electrical engineers moved on and had to do this stuff. And so it's good prep for all of you should you engage in that kind of coding later on in life. This may trigger an interest for some of you in it. So we'll target a thermometer, which is a simple little device. This pretend thermometer has several features to it. It has a temperature sensor in it, which reads some sort of environmental factor that indicates it's hot or it's cold out, and has digital signal in that. Unfortunately, that signal needs to be converted into to get it to what a human consumer would sort of look at as displayable information of degrees Celsius or degrees Fahrenheit. So there's a control port for this, which says, should I display the information in Celsius or Fahrenheit? And then there'll be some code that you need to plop down that does the conversion, along with a little simulator and a make file that says, take your code, plug it into the simulator, so it can do that. Now, it's very common for little embedded devices like that then to expose things like their sensors as, for instance, a global variable. To say like, oh, if you read this global variable, it's tied to the wires that go out to the sensor and is constantly then updating with what does the environmental factor say about the temperature right now. Oftentimes such sensors, they aren't in like normal units, that they involve some conversion, and this pretend one that's given here is in units of 0.1 out of 32 degrees Celsius. So that is, if you multiply this number by 32, you get 1/10 of a degrees Celsius. It also has a limit to the range of temperatures it can detect, down to minus 45 degrees Celsius, which is very, very cold, and up to 45 degrees Celsius, very, very hot. And so that'll have some practical ramifications for if the sensor reads something that's sort of out of this range, then something's gone wrong and you'll want to detect an error. So to do those conversions, it'll involve a little bit of math. And while it's stated here as a fractional value, for cheap microcontrollers, like the one that would be in a thermometer like this, they actually don't even have floating point units in them. So everything will be done in integer values. And we can get around that constraint just by saying, oh, this is going to read not 45, but 450, or minus 450 in this case. And rather than 1.0, this will be 10. So the units we'll use here from tens degrees. Some of the sensor values and their corresponding degrees in Celsius are over here on the right-hand side in this table. There's nothing that you need to read too deeply into this other than some error check values here. But there's a prescription given then to the math that has to do with that's how this thing works. In addition to that then, there's a little global variable that indicates some buttons that are either pressed or not pressed on the device. And the only one that's of real concern is whether or not the temperature is supposed to be displayed in Celsius for the rest of the world or for Fahrenheit, which is basically the United States these days. If you're building such devices and can manage it, it's nice because you could then sell this thermometer to the entire world there. Now that information, whether or not the button is pressed, is essentially binary, and so only a single bit needs to represent like on for or off for Celsius, on for Fahrenheit there, button pushed or not pushed. And so there'll be a single bit in this 8-bit variable, this character, that indicates display in Celsius or display in Fahrenheit. The remaining bits may be on or off, but we don't care about it. And so this will be a good opportunity to make use of some of the bit shifting techniques to say, I need to fish out this one individual bit. Can't look at the entire thing, just this one spot, because that's what's going to dictate how I display things. Finally then, the other sort of C-level feature that's exposed here is one final global variable that has 32 bits in it as an integer. However, these are not to be interpreted as a number. Rather, the bits in this 32-bit quantity are tied to LCD panels that are either lit or not lit in order to display information. To give you an idea, here's what you can do with 7 bits if you tie the output voltage of those things to some little lights over there. For instance, if you had an 8-bit or 7-bit quantity like this, 0 up to bit 6 here, and left off bit 2, but left the rest of them on here. These are tied to little panels so that if there's a 1 in there, it'll light up the panel. So here's panel 1, it's tied to this one, so over there that would turn this on, versus panel 2, there's a 0 here, so leave that one off. Then you can draw something that looks vaguely like a 0. Hopefully all of you in your real life experience have seen little LCD panels like this. It's sometimes referred to as a 7-panel display because there are 1, 2, 3, 4, 5, 6, and then the 7 middle bar here. But it allows you basically to draw renditions of digits like this. And they're oftentimes then controlled with bits like this. Plop down a bit string like this, and it'll display a 0. Plop down a bit string like this, which is not the binary representation for 1, because it has a couple 1s in it, but it will turn on certain panels so that it displays something that looks like a 1 to a human who might be reading it. The patterns for the remainder of the 9 digits, or 10 digits that you want, along with a few other things like a negative sign and an E and something that looks kind of like an R, so you can spell out air in some cases, they're present here and are worth your consideration as you look through this thing. The remainder of this then gives some idea of how this could combine if you were given a display, and this is essentially what the thermometer display looks like. It's got 4 possible digits here. that will allow you to display information like an 8, a 3, a dot that's over here, and a 9. The dot's always on. And then either a Celsius that's on or a Fahrenheit that's on. And you'll see over here some of the bits, they are actually tied to whether or not those things are on or off. Essentially, then each digit is just stacked like, these low order bits in the 32 bits integer that comprises the display. It would control this rightmost digit. The next 7 bits over here, they control a middle digit. And the next digits, they control this left digit over here. And since I didn't want anything else, this leftmost blank is present there. So there are several different sort of examples of this given with different bit patterns over here. And while it looks a little intimidating, it's really just a matter of constructing a bit string that looks like this so that a 5 goes here. And then shifting some bits over and plopping down a pattern that looks like this so a 0 shows up over there. Your objective in this project then is to code 3 separate functions that combine to read the information from some of these global variables and then plop down in this global variable a bit sequence that would cause a display to look something like this over here. And the simulator will provide that for you. The 3 functions, and here's where we can start copying some stuff from the project spec into the file, would be great, are set temp from ports, which is generally designed to read in some information from that global sensor temperature thing, as well as the status port that says Celsius or Fahrenheit, and construct one of these little structs that say what's my actual temperature and which mode am I in, Celsius or Fahrenheit or an error mode there. The second function is then we'll take one of those structs and then convert it into a bit string that is to be put on the display. So lay down a bunch of 1s and 0s that will show a pattern of 98.3 Fahrenheit to show that it's a very hot day, 98.3 degrees Fahrenheit. And then one final function that is meant to be run repeatedly, a thermal update, takes arguments, just looks at global variables, and runs those 2 other functions that are over there. So the first step to getting this project started for problem 1 is to create a file that has those 3 functions in it. And so I will have to do a couple things. I'll maybe copy paste this thing so I get some of the stuff there. Let me find here. Let's see. Okay, I gotta remember that this is called a certain name on thermoupdate.c. So let me create that file, thermoupdate.c, and I'm just gonna copy this stuff here. And I'll paste it in here into my code editor. Now this is a prototype for a function. It's not an actual body. But we'll fix that in a second after we do some more copying and pasting. I don't need the struct here because that's in a header that we have access to and can include in just a second. Let me copy and paste this one. This is good. And then I need that final one here, which is thermal update. Copy and paste this one. Okay, if you buzz around over here, you also see that there should be a thermo.h file, which is the header file associated with this problem. It has the struct recipe for that temp t struct. And so I'm going to up top as well pound include that thermo.h here. You'll notice there's a distinction in C programs between using double quotes for pound includes and the angle brackets. Generally, for stuff that's at a system level, like stdio and stdlib, use the angle brackets. The double quotations here, therefore, I don't know, I wouldn't say self-defined headers, but it's sort of locally stored headers, and this one's in the present directory, so it's appropriate for that. We may have a chance to talk about that a little bit more later, but it's not necessary right now. Okay, now having done that, if I try to do the make test problem 1 again, I'll still get errors on this because there's complaints that several functions are undefined. And if I make this a little wider, we say set temp from parts, set display from temp, thermal update. You might ask, like, what gives? Well, the reason is that, again, this doesn't actually define the function. It's a prototype that says such a function exists and will be provided to you at some point. And we may want to fix that right now because we actually want to run the tests. And that's as easy as giving this thing a body. So I'll leave the commentary here because I think that's worth having. The only obligation that this function needs to fulfill is to return an integer. And so I'll return a default integer like a 0 to begin with. And so I can do likewise for these other things. Now this seems like a cosmetic difference, but it will cause the compiler to actually generate, here's a callable function. All it does right now is return 0. But that fulfills the requirement that such a function now exists and can be called. This is also an int one, so I'll return 0 here. And with that change, I should be able to actually run the tests. Now, I won't expect to pass any of these right now, but it will give me sort of a fighting chance to start, now I can start looking at what is this first function, set temp from ports, actually supposed to do here. The careful reader will look at this and see, there are 40 tests here. That's actually quite a few tests. For this problem, each test is worth a half point. And so the scoring of this will be scaled. There's 20 points associated with the manual inspection criteria for this. And it's worthwhile then to look at the end game of what this thermomain is actually supposed to do, because that's the simulator thing over here, 0 out of 20 so far. So that program gets built, if you didn't see it go by fastly, this is thermal update and blah, 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 all this stuff. And yeah, this thermomain here is the sort of main program that's built. If you want to play around with this thing, thermomain here, you plop something down, the sensor, and you require a sensor value and whether you're going to put this in Celsius or Fahrenheit mode. Let's see, according to this down here, well, I used to have a weather app down here and it went away. I guess I'll need to refresh this or something like that. I think it's about 68 degrees out Celsius or Fahrenheit right now, so I might think to write 68 Fahrenheit here. Unfortunately, this is actually a raw sensor value, and so I'll need to multiply that by 32 and then do some other conversions to get the actual, like a Fahrenheit value there. So I'm just going to pick up an example that's coming from the example table that's up here. It's a little bit easier. For instance, this one's supposed to be 10 degrees Celsius, and I actually don't know what that is in Fahrenheit. This isn't going to tell me, but I'll plop down that as a sensor value. So this isn't the number of degrees Celsius or Fahrenheit, it's instead a sensor value that's to be used there. So running this thing gives an interactive display here. You can see not much is doing. The program itself will go through and call the various functions like your set temp from ports and set display from temp, and then produce some outputs, including things like, here's the bit string that you constructed to put a display on the screen. It's got all zeros in it, which means then down here, as the graphical display would show up, that doesn't look like anything right now. Eventually, once you complete some of those functions and make some headway, you'll start to get stuff that looks sort of like the following. These are down here in the sample runs of thermomain. That correct looking stuff will be like, at sensor value of 0, this is the absolute lowest temperature that can be seen. I run thermomain, and what goes onto the screen is this 45.0 degrees Celsius. And that's created from the fact that, over here, there's a pattern of ones and zeros. So that's what's going to go out to the display. And look, everything's lit except this middle one is missing. That corresponds to this thing, and that's why this looks like a 0 instead. Versus this next left sort of collection of 7 bits. There's a couple missing here, and that corresponds to this spot and to this spot, and that's why this thing looks kind of like a 5. To construct this thing, there are a bunch of tips in the project specification, in the set display from temp discussion over here. One of the key tips is to take all these bit strings that are mentioned up here and plop them down in an array, so that at the 0th element of the array, there's a bit string that looks like this. And at the 2th element of the array is a bit string that looks like this. This will allow you to say, as I'm taking my 3-digit temperature and figuring out the right digit should be a 2, I'll go to index 2 of an array and fish out this bit string and plop that down in the display so that a 2 goes onto the screen. For more details on that, have a close look at the advice that's given there. But this should be enough to get you started running, because you'll now be able to run the tests and start following some of the instructions about how to go about writing those functions. Most folks don't find this to be a terribly difficult problem, just it takes a little bit of time to wrap your head around the bit shifting, oring, anding business that is central to it. Okay, the next problem is one that doesn't actually involve you writing any code. Instead, this is debugging exercises. And if you've been following along with Lab 5, you'll have seen one of the phases of this puzzle that's going to be in use and made use. It's a program called Puzzlebox, and it's centered around getting you to make use of the debugger. So GDB is a favored debugger amongst those who code in C. And it's what we'll prescribe for use here, but if you happen to have experience with another debugger, you're welcome to use it. GDB is widely available and is extremely, it's extremely likely any program environment that has a C compiler on it will have something like GDB around it. But it is a command line utility, and so it takes a little bit of getting used to. My hope is that the lab this week, as long with the instructions that I'll provide now, will give you some sense of how to go about doing this. So the program that's provided to you called Puzzlebox is one part of this. The other is that you'll have a little input.txt file that's here. And the general nature of this is we run Puzzlebox, and it's going to read information from this input.txt, use it, and attempt to sort of satisfy some constraints that are in the program to move you ahead between phase 1, phase 2, phase 3, etc. The more phases you pass, the more points you get. The nature of the program is intentionally somewhat confusing in that looking at the source code for Puzzlebox, it's not immediately obvious what numbers or letters or strings that you actually need to input in order to pass through phases. Instead, it's by virtue of using the debugger to sort of step through things there and saying, oh, this data was transformed in the following way. I don't need to know exactly what the transformation process was. I just know what it looks like now, and that will dictate what I should put in this input file in order to satisfy these constraints that I'm seeing that the phase is desiring. Okay, so let's play around with this quick. First things first, if I buzz over here, I should do a make, I think it's prob 2, and that will build Puzzlebox here. If you were to run it, Puzzlebox, it requires an input file, and as is indicated in the specification, if you run it on the default provided one, this input.txt here, maybe get my shell over here. It's going to immediately reject this because the first thing you need to modify is to plop down a directory ID. At least this is the name that I've heard students ascribe to the first part of your @terpmail email address. It's what you use to log into Canvas and so forth. I'll pretend for the moment that mine is cough0095, as most of these have a limit of 8 characters, as well as being a combination of some part of your name and maybe a number or something like that. I gather that students can actually change this, which is kind of nice. My last universities, I couldn't change it at all, which led to weird results as a professor, but no matter there. So if I rerun at this point, then at least that part will be accepted. But I won't make much progress because I get stuck at this phase 1, which apparently is rejected there. Now, one possible path to this is to start looking at the puzzlebox.c code and finding, for instance, this phase 1 business, phase 1 here. And what you'll see is that there's some input taken here from the input file. In this case, it'll be 1, 2, 3. The first thing is read is this, and we'll talk about what it's used for in just a second. And then some of that input, like this A number, is modified using something called hash. Hash, if you read through the code somewhat, is a number that's determined based on this directory ID. And it has some randomness to it in that my directory ID, by virtue of being cough0095, will generate a different hash value than your directory ID because those are unique. And so your path through this will be similar to other students, but the values you need to enter will probably be somewhat unique based on that randomization based on your directory ID. So in this case, I could do the calculation myself, like figure out what is my hash value. That's printed out at the top of the sort of run here. Here's hash value by here. So I could do the mod 41 and then do some calculations here. My suggestion is to start this now because it'll be true as you go forwards in this, that actually the debugger can do that for you. You don't have to worry about it. So it would be a good time to sort of fire up the debugger and show how to set a breakpoint here and sort of stop time and poke around in this thing. And they'll give you the general workflow for that. I find it's a little easier to run this in a proper full terminal, so let me fire one up here. And for some reason, it always starts in the background, but no matter. I'll make this a little bit bigger. So here I'm in P2 code. I want to debug this program called Puzzlebox, set breakpoints, etc. in it. And so the invocation that's typical is to use GDB, that's the name of the debugger, then -2e. This will put GDB in the text user interface mode. It can also be in plain command line mode, which is slightly more convenient for some things, but most beginners have an easier time being able to see code while they do things, so the text user interface is going to be better for that. And then the program that I want to debug is called Puzzlebox here. Yeah, okay, so this fired up. I have to press enter once or twice to get this to go through. But then up in the top pane here, I'll see source code. Up and down, we'll sort of scroll up and down for that part here. And then down at the bottom, I have a command line window where as I type things, that'll show up over there. Debuggers are cool because they allow you to stop time. Generally speaking, you can run programs, but if you don't set any breakpoints, then the program will just sort of run to completion, possibly stopping if there's a segmentation fault or something like that. We don't want that to happen in this case because if I ran, I'd just get more or less the same results that I got over here. Instead, I want to stop time at a specific spot. The easiest place to put breakpoints out of the gate is at function boundaries. So there's this phase 1 function that's going to call at some point. I'm going to set a breakpoint there, phase 0, 1. And this will cause the debugger, when I'm running, to stop time when you arrive at a call to phase 1 and allow me to then poke around and see what's happening there. There are two ways then to run at this point. One option is to say run, and since this requires a command line argument, I'd have to say run inputs.txt. I find that a little bit cumbersome for repeated debug sections, so I'll opt for the other way to say set the command line arguments, say input.txt. And that way, every time I type run, it'll say run with this as the command line argument to Puzzlebox. So if I run at this point, yeah, go ahead and do that. And after a couple sort of presses of enter, I land here. And you see the capital B here. This is a breakpoint that's been set. So anytime I'd hit this line of code, the time would stop and I can poke around in GDB. For instance, I might print out what is the value for A, what is the value for B, what is the value for C. These are all uninitialized. The debugger knows there's stack space allocated for them, but they have random values in them at this point because I haven't actually executed the code to populate them. There are a couple different ways to move forwards in time and almost no ways to move backwards in a typical debugger. I find for C programs these two to be the most useful. Next will move you to the next line of code. Importantly, it passes over any function calls that are there. So for instance, this line has two function calls on it, next inputs and A to I. I don't really care about this because this function is provided as part of Puzzlebox and is supposed to read something from the input file. We'll read this 1 over here. And I can make this a little bit smaller to see that on the left side. And I don't really care how it does that. Just know that it comes in so that as I would print out what is A now, it's 1. And if I type next again and printed out B, rather than its uninitialized value, it's got a 2 that's coming straight out of this thing. And a shortcut, I've typed next, so if I punch enter, it'll just rerun the next command. So if I print out, I'll have to type next again. And I print out C now, it'll be 3. I can keep sort of nexting through this thing, and that's all fine and good. But at this point, it would be good to check here. A was modified in some way by this random hash value modulo 41 over here. So if I print out what A looks like now, rather than 1, it's 36. The check that's about to happen here is whether or not A is less than B, B is greater than C, and A is less than C. And if I next one more time, you'll find that's not true right now based on the input values that I provided. So I'm about to bail out and lose, points. At this stage, it'd be a good idea to use reasoning skill to sort of determine, okay, if A started as 1 but became 36, B and C, they aren't modified at all in here, so I can plop some values down here and actually get this set of constraints to be satisfied. So clearly A is less than, let's see, A is less than B here, but if A becomes 36 on adding the hash value over here, I need something that's bigger than that for B. So maybe I bump this up to 37. B has to be greater than C. Well, it is right now, it's 3, but then A has to be less than C as well. So that doesn't fly because the 1 becomes a 36, and that's not less than that. So I'll make this 37, and I'll make this 39, or something like that. Now, I think mentally that this is a good show. And so what I want to do now is to rerun from the beginning. And I'll just type run again to do so. So kill the current run, and there'll be a prompt to say, are you sure you want to stop progress and restart from the beginning? I am indeed in this case. And I will then see, first, there's some screen tearing that happens here, which oftentimes happens with these text interfaces. You'll find yourself jabbing Control L. That's hold the Control key and press L often, which redraws the screen so that you see this a little better. And we hit our original breakpoint here at the top of phase 1. I'll type N, which is short for next, and then punch enter a bunch of times because I want to sort of zip forwards to this point. And at this point, I print out A, print out B, print out C. This is all looking like this stuff should be satisfied. So if I next one more time, I'm about to return. And this case, I'll buzz out of this and earn some points here. One other common sort of command to use is to continue. This will continue execution until the next breakpoint or stop or run to the end of the program, which will be the case here. If I punch that, then you'll see, I didn't make it any further, but hey, I earned 3 points now on account of having passed that first phase. This output down here is what's actually sort of causing the screen to go haywire. So if I press Control L, I'll get the screen back, but I'll lose that output. And you can verify in a normal shell then over here that if I run this thing, I've earned my 3 points over here. Essentially, that's all that make test prob 2 does. Is run puzzle box on your input.txt. Now the next steps would be to sort of get rid of my breakpoints, delete. Let's see, I can get information on breakpoints, info break. So breakpoint 1 is here, and I'll delete that, delete 1, and maybe set a breakpoint now at phase 02. And if I give a run at this point, I'll find myself in phase 2 and can begin analyzing how many inputs do I need. Looks like 3 again here. And so I should probably put down another 1, 2, 3 here, as those will come in then as input from this thing. And then start to look at what modifications are going to be made to this set of stuff. As well, then what do I need to enter here to satisfy the ultimate constraints that are down here that are going to be looked for. Oh, no, there's a little go-to here, which is a reminder of things to come soon here. Again, not code that you want to write yourself, but here it's designed pedagogically to remind you a few things. Okay, so that's your basic work cycle for this puzzle box here. There's one tip that I think is worth mentioning, that occasionally if you want to get your shell back but not lose your debugging section, you do well to learn the following keystroke, Control Z. So here's my terminal, I press Control Z. This will suspend the program that's currently got control of the terminal and flip it into the background for the moment. It gets me my shell back over here. I can ask about what jobs are presently running in the shell, and you'll see GDB hasn't gone away, it's still over here. And should you want to return to this job over here, typing foreground will bring back the debugger over here. Folks have been operating in shell environments like this for a long time, and so there are many conveniences built in the shell, although they're a little bit inaccessible to beginners. So again, that's Control Z to suspend a program. And then as I'd want to know what programs are running, I type foreground to bring in this most immediately suspended, or FG1 to say I want to specifically bring this one back up. So if you're working purely in the terminal, as I often am, this would be Emacs NW to say open up Emacs and show me what's in the current directory. I do some stuff here, then I press Control Z, that flips me back to the shell. Ask what jobs are around, and I say foreground the debugger. That's GDB here, job number 1 with this little or the percent sign short for jobs. I'm back in the debugger. I do some things here like next a little bit. Then say I'm done here, Control Z to flip back to the shell. I want to know what jobs are around. Let me foreground Emacs this time, and I'm back in Emacs. So with relative quickness, then you can flip between those things. Okay, that's about all we want to do with by way of introduction to problem 2, and then we'll spend just a moment on problem 3, which is the real bear. I should say a lot of folks kind of like puzzles like this. If it's not your cup of tea, don't worry. As well, there are more phases to Puzzle Box than are strictly needed to get full credit, and there's let's see, I think what is it, 40 points or so, or 30 points available, but you can get up to 40 by in there. Let's see, I think I might have to adjust some terminology here that it's actually a 30-point problem. But that means there's some makeup credit. So if you solve the last few more challenging phases, you can make up for lost credit on project 1 or on future projects like 3, 4, and 5, etc., or on this one if you happen to not do as well. But a lot of folks find puzzles like this fun, and just bear in mind it's usually a good idea to read instructions and get acquainted with GDB out there. Okay, the last problem is the one that will probably cause some stress for some of you. It's a typical C applications programming endeavor, and the idea here is just to build a little interactive application that manages a hash map. Hopefully, you have taken a course that has educated you a bit about hash tables in general, and possibly drawn the distinction between sets and maps, sets being a collection of unique objects, maps being a map from a key to a value. They have wide applicability in computer science and are most often backed up by 2 types of data structures, either a hash table, which can be used to create a hash set or a hash map, or a binary search tree of some kind, oftentimes a balanced one like red-black tree, and those are used to create a tree map or a tree set. I like Java in some ways, and one of the ways I like it is that they have direct names for those things: tree set, tree map, hash set, hash map. There are advantages and trade-offs to both of those backing data structures. So our idea here is to pick one specific instance and implement it so that you create a little hash map program that's called hashmain. And all it does is say, oh, you can put keys and values into the hash table, and then print out the entirety of it, and see, oh, here's a key that was put in here and the value that's associated. A key and a value that's associated with it. Now you notice there's no ordering here in the printout as to the reflection of what order things were put into the hash map. And that's one disadvantage of hash tables, that there really is no ordering, not alphabetic, not order of putting things in unless you do like other special stuff there. But the payoff for hash tables is that they are generally constant time to add something and constant time to look up or remove something. We won't bother with the remove part here, but just the put something in and look it up. And that's why they're a favored data structure in many cases, constant time operations. So for instance, we've got Dustin in there, and if you ask to get what's the value associated with Dustin, then it'll be Corny, because that's what we put in there before. Whereas if you ask to get a key, Jim, that's not been added in the hash table, then it'll print out a message about not found there. So at any rate, this little interactive application then is going to be divided in a similar fashion to the linked list application that was the subject of Lab 2, where there'll be one file that has the main function in it, and it's essentially a big loop that takes inputs and figures out what to do with the hash table, and then calls an appropriate function that's in a hash map funcs.c. That's actually a C function that will manipulate the hash table itself. If you're not familiar with hash tables, it'd be a great idea to do some reading on this, and we'll specifically focus on separate chaining using linked lists. It's probably a good idea just to pull up a quick table over here. I think over here So this is the picture of like a separate chaining where you go to an entry in the hash table, and what will be there will be either a null or a pointer to a node. And if more than one key maps to this spot in the hash table, then this starts a linked list of all the things that are in there. And to that end, you'll see those reflected in the data structures associated with it. If that's new information for you, do some studying now so you can get acquainted with it. Very commonly used technique to manage hash tables where there's not going to be a unique entry here for everything you could possibly put in the hash table. And so you need to deal with these collisions of like, what if two things map here? Well, just put them in a list over here. Okay, other things to talk about here. I think the getting started part is the most important. So dealing with this data structure bit of business, you may want to have a look at the header and find there's something in there that looks a lot like a linked list node, because that's what it is. Just has two kinds of data, a key and a value, because we're putting keys associated with values in it, as well as then a housing data structure, a Hashmap T, which has what amounts to an array of node pointers in it, as well as some features like how big is this array and how many things have been put into the hash table. One important optimization associated with hash tables is to say when the table starts getting full, like it's 10 entries big and I've got 8 things in the hash table, you usually, to preserve the performance of the hash table, expand the array so it's bigger, but that requires rehashing everything and possibly putting it down at new locations. This is in the header and don't need to sort of pay too much mind. What's of more import is this list of functions, as it comprises what's a bare bones sort of required version of this stuff, where we'll be looking for these functions and assigning some manual inspection criteria to grade them, so they should be in there. I will provide the hash code function here. I realize it isn't in here, but I think it's down below. Yeah, you copy it in over there, so we'll do that in a second. But just like we did for the first problem, this is the outline of one of the files that we need to create, this hashmap funcs.c file. And so I'll initiate this process by creating that file and then plopping those functions down and possibly filling in some values or some bodies for them. So here's hashmap funcs.c. And as I go through, I'm going to grab then all of this stuff here. Okay, and that stuff there. Copy that. Yank it in. As we did before, I'll probably want to put in a pound include. The name of the header in this case is up here, hashmap.h. So copy paste magic there. Now again, these don't have bodies to any of the functions yet, but I can fill those bodies in later. The first one's easy because it's actually provided. It's part of the program specification here. And so I'll take this body over here, which you're not required to understand, but is extraordinarily useful to understand for your long-term C development. So this will be the part of this that's is what constitutes that body there. It's important that you make use of this hash code function as the test results expect it to be used. And while there's considerable variety in what hash code functions can look like, this one's prescribed and required right now. So don't use something else, even if you want to, use something else on your own time and sort of experiment with it. That's only half the battle. If you come back up for just a moment to the download setup, there are two required parts to this, the hashmap funcs, and we've got a start on that, but also a hashmap main up here. Now, this can be a little bit intimidating to write out of the gate because it's supposed to have a bunch of features, an input loop, data structure, and so forth. But there's a nice shortcut to this. We did a lab earlier that is very similar to this in terms of structure involving linked lists. And so what I'm about to do is an oft-used technique to say, I've written a similar program to this before. I just want to get that old code in and start adapting it to this new situation. So it's a good idea to find that code. If you think back in your memory a little bit, say, okay, where exactly did we do that in terms of the class? You should turn your attention over to Lab 2 because this is where we had a linked list application and there was a list main and a list funcs. This is the same structure that's used for the Hashmap stuff. So to that end, I'm going to grab this Lab 2 code here. Let's see, copy the link address, zip over here to my shell, and do a wget here. Actually, I don't want to put this in my project directory, so I'll do it here. One directory up in my directory. So if I look here, that gets me my lab2 code.zip. So if I unzip that, lab2 code.zip, that should create a directory. And here is that list main.c file. It's all like ready to go. Now, clearly this isn't usable completely because it makes use of a list T data structure, which we're not going to use. It's a Hashmap instead. It prints out I'm a linked list demo, and that's not right. It's supposed to be a Hashmap thing. The prompt is wrong, etc. But there's a lot of really usable stuff in here. For instance, just like this version of the main, the Hashmap main that you're to write is going to be required to do this command line echoing thing. And it's sure a lot easier to sort of copy that from over here than it is to reinvent the wheel yourself and sort of write this from scratch. So I'll do a time-honored thing. I'll just make a copy. So here's copy lab02 code. And I'll put the list main.c, that's the name of the file, that's the original. I'm going to copy this into p2 code, and I'll call it hashmap main.c. So if I come back up over to the project 2 code now and refresh, here is a hashmap main.c. It's a direct copy of that list stuff. And I can't compile it right now because it has a bunch of things that are wrong with it, but I can start making some changes. For instance, this will be hashmap, or is it hash? I can't remember. Hashmap.h, that's cool. I might make this then, if I looked in that header, I'm not going to want a list T struct, I want a hashmap T struct, so here, so hashmap T. And I might call this hashmap, something like that. I don't know about this function yet, so I'll just comment it out. And let's see, other things I might notice later on, that's fine. We're pretty close to compile right now, but there's a bunch of functions in here that are no good. So I'm just going to start commenting some things here. And for instance, I don't need to do the actual list getting and stuff. Some of these might have some equivalents, so I won't clear it out. I just want to comment out the things that are in here that don't correspond to hash operations. Because my goal right now is to just get this thing to build, and then that'll enable you to start running test cases and filling in definitions and so forth. Let me just do a quick search for list stuff here. It's not very easy to read when it's big like that. This is all commented out, so that's looking pretty good. So if I buzz back over to my shell and I just try make prob 3, I guess there's, I'm in the wrong directory hand. Let's see, p2 code. Yeah, that's what it is. And so make prob 3. I'll make hash map. I should have a prob 3 there for all of you. Okay. I spelled hashmap wrong. God, that's terrible. Okay. So hasmap.t. That's okay. That's an easy one to fix. It's just a hash here. Make this, and it's an unused variable. What do I want to do here with that? I'll just comment it out for right now because I don't feel like dealing with that warning. Ith undeclared, I don't know where that is. That's line 63 here, so 63. Ith is undeclared. Oh, I see. I'll just put down a car star ith equals null. I mean, this is definitely something we're going to have to fix up because there's probably a different set of semantics for get for this, but don't matter there. Again, just trying to get this to compile. Let's see. Now I got trouble here. Hashmap right, unknown type file. Okay. I wonder in my funcs, did I forget? Nope. Okay, so I just need to include probably these other things over here. Should have put those in hashmap.h, but no matter. Unknown type here for file star. This is in hashmap funcs. Let's see, unknown type file. Here I included my stio.h, so I'm not sure where that thing's happening. Say file is defined in header. Did you forget to do that? I feel like I didn't forget to do that because it's right there. I wonder if there's some weird, ordering the header files that I messed up here. Yeah, there is. Okay. Well, my bad, gang. That if you write a good header file, and clearly I didn't hear, the order's not supposed to matter. But it apparently does, and I'll try to correct that as we go forwards and get folks that part. So, but hey, look, we've got a Hashmap main application now. So if I run that here, main, it looks like a list application. It doesn't do anything like insert apple and print. Like it's not going to do anything right now. But the beauty of this part is that I can now let's see, run make test prob 3. And this will give me a whole bunch of failures, but hey, I can run the test cases, and that means incremental progress towards victory. I'm even, getting something that's a correct echoing behavior because I included the echo from the original version of that. Okay, so generally speaking then, this is harder for a couple reasons. It's a somewhat more complex data structure to manage. As well, if you look at these tests, they're actually not unit tests anymore. They're closer to what's often referred to as integration tests, as in order to test whether this hash table thing works right, I have to be able to put something into it and get something out of it, and I need to be able to have a little main routine that does that kind of stuff. That's actually 3 or 4 different parts that have to coalesce together to form a working whole. Now, oftentimes folks will look at this and say, but I wanted tests that tested individual functions. Like, where is my test? Let's see, not for this project. Oh, yeah, I got to move forwards here. Crap. Okay, back to project 2. You gave me all these functions here that's in this little outline, like hashmap put. Where is my test of hashmap put? This is a misunderstanding of what a unit test actually is. This hash table is a unit. There's no way, if you want to maintain abstraction barriers, to say I can put something into it and then test that it succeeded, unless you have some means to either break the abstraction barrier and know underlying the hood, this is arranged the following as an array and I should look for here in it, or instead this other function, hashmap get, also works. So as a unit, the hash table then is something that needs to be tested in its entirety. And so properly written tests would say, I'm going to use a put and a get because the get determines whether the put is right. But that means if I have a bug in one of these but not the other, then I don't know which one from the test is actually problematic out there. And so folks will need to sort of look carefully at that. You have to build parts of your hash table to say the put and the get together, and then look at the sort of functionality overall to see it. And that's more or less what's reflected in the test cases that are provided. They don't provide as much insights specifically into the problem is in this function. But that'll be good training for you to be able to read the tea leaves that Valgrind provides and reason about the data structure itself to try to determine, okay, I think the problem is here. I'm going to add some print line debugging. I might fire up GDB, and after I put things in, go poke around in the array that's there to see what's present. And that's generally good skills to have that only come from working on a slightly larger application like this. I encourage you to start early because oftentimes folks whiz through the first couple of problems and don't then sort of pay much attention until the last minutes to this last problem, which is somewhat more challenging here. And as you would want to talk about internal architectural decisions like why did I pick this particular hash code? Are there alternatives? I'm very happy to do so. Just wouldn't be necessarily solving test cases in that case. As before, when you are done, it's as easy as typing make zip, and that will create a P2 completes, which if you get off of Grace and plop down on Gradescope, test case will run, and you'll be good to go there. I think that's all I have to say for the moment, and so I will bid you adieu. See you in your lecture, and happy hacking on this one, gang. Catch you later.